Hello everyone and welcome to The Algorithms. In our last video, we discussed about the articulation points in a connected undirected graph. And today I am back with another graph theory topic which happens to be very closely related to the articulation point, and the topic is going to be finding bridges in a connected undirected graph. I would highly recommend that you please go through the video where I have discussed about the articulation points, because I will be using a whole lot of concepts introduced in that video to discuss about how to find the bridges in a connected undirected graph. You can access the contents we discussed on the articulation points in two ways. You can either go to our YouTube channel, The Algorithms, and here you can see the first video from the left is on the articulation points, or you can go to our website, thealgorithms.com slash algo, and from there you see the series we have on advanced graph algorithms. From there, the first topic happens to be articulation points, so from there you can access the contents on articulation points. So let's now see what are the bridges in a connected undirected graph. A bridge is an edge if the removal of the edge makes the connected undirected graph disconnected. So the undirected graph is initially connected. We remove an edge if it becomes disconnected, and it is divided into two different components. Then we would know that that edge is is a bridge in that given graph. So for this graph, you can see the bridge would be the edge uv, or you can take the edge from any direction. You can even say the edge is vu. It does not matter, because if we remove the edge uv, the graph will become disconnected. So let's remove the edge, and now you can see that we have two different components and they are disconnected, and we got this by removing the edge that existed in between the vertices u and v. So the edge uv or vu is the bridge in this given graph. So next we will discuss how we can actually find out what are the edges in a given connected undirected graph are acting as a bridge, and we will do that in the same way as we did in the articulation points video. We won't assume that we already know the algorithm. We would actually start from a clean slate, and we would find out the different rationales and logic, and we would make different observations, and using those observations we would come up with the algorithm. But as I said, we will be using some of the concepts we have already introduced in the articulation points, and we won't be doing some of the foundational discussions we have already done in the articulation points tutorial. Uh, because my assumption is you already have gone through the video we have on the articulation points, and you have the idea about when and how we use discovery time and what does it mean. And my assumption is you also know what does lowest node reachable from a node mean. The new concept introduced for computing the bridge is this part without using parent. let's try to figure out what condition actually makes an edge a bridge. So, in our example graph, the edge UV is the bridge. So, let's see, as we have already seen, what happens when we remove the bridge. We get two disconnected components, and this also we have covered in the articulation points discussion, that what could have avoided the graph to get disconnected. And the answer is, if we had any edge that would have connected these two component. So if the given undirected graph had any edge, say an edge like this, now we see we have removed the bridge, we have removed the edge UV, and the graph is still intact. The graph is not disconnected. So now, if we remember about the DFS spanning tree we constructed for the articulation point, if we construct the same DFS spanning tree, then that would mean that for any age we are considering, so let's say we are considering the age UV right now, and we have and U was discovered before V. So if we see that the subtree, or in this case the subgraph rooted at V, is connected to any of the earlier discovered vertex, then we cannot say that the current edge that we are considering is a bridge. And what I mean by that is, currently we are considering the edge UV, and we are saying that U was discovered before V in the DFS spanning tree. So say the DFS can be something like this. We discovered the S first, followed by T, then we discovered U, and then we have discovered V. And let's not worry about the subgraph of V right now. So let's suppose V has some subgraph, but those have already been processed, and we have backtracked to V, and we have also processed V, and we have processed all the so we have processed the whole subgraph rooted at V, which means we have processed all the adjacent vertices of V and all the descendants of V, and we have even backtracked to U. So from V to U, when we backtract, then if we see that the subgraph rooted at V, so the V and its descendants, they can somehow reach either U or any of its ancestors, either this one or either S or T. So if we see that V can reach at least U or any of the earlier discovered node, then we would know that UV is not a bridge. And why is it so? So let's take case by case here. Say if W was connected to U, so even if we disconnected the even if we removed the edge U V, then also the graph would not have been disconnected. So you can see, yeah, because of the back edge W U, the graph is not disconnected. Or if um, the subgraph rooted at V was connected to S or T, and if you look at um, the discovery time, S and T was discovered before U. So if the subgraph rooted at V, if that subgraph is somehow connected to either S or T or U, using any back edge, then we cannot say that UV is a bridge. So in general, we will have to see whenever we backtrack from a vertex to its parent. So like say we are backtracking from V to its parent U, then I just need to check if V can reach to at least U or to any of the earlier discovered vertices. Now it is very important to note we cannot use the back edge VU while we are checking if VU, if the edge VU is the bridge or not. So while this is a very important part of the algorithm, and we need to keep in mind while writing the code that when we are at V, computing the earliest discovered vertex that is reachable from V through its descendants and using at most one back edge, we should not use the parent, or we should not use U, because U happens to be the immediate parent in the DFS spanning tree. So we know that we reached V directly from U. So U is the parent of V, and that is exactly why we will be backtracking from V to U. So while we are at V and we are computing the earliest the earliest discovered node reachable from V, we should not use the edge that connects the current node, and the current node is V here, that connects the current node to its parent, and the parent here is U. We need to keep this in mind while implementing the algorithm. And in articulation points discussion, we have already discussed that how we compute the earliest discovered node reachable from a node using its descendants and one back edge. And we have already discussed that if one of the adjacent node happens to be an ancestor in the DFS spanning tree, then we check with the current earliest discovered node reachable of the current node with the discovery time of the adjacent node, which is an ancestor, and we take the minimum. And if the adjacent node is not an ancestor, then we compare the current earliest discovered node reachable for the current node with the earliest discovered node reachable from that adjacent node, and whichever is minimum. So let's recap what we just discussed. We have this given tree, like given graph, and from there we are trying to uh, find out all the bridges. So um, we know uh, we can see that the edge uv is a bridge, and what like makes this one a bridge is that when the bridge is removed, we have two disconnected components, and they are not connected to each other. Like that is what makes that edge a bridge. So if we take a DFS spanning tree, we need to check for every edge, say UV, where U was discovered before V, that the descendants of V and including V, what is the earliest discovered node using at most one back edge, they can reach 2. If we see that V um, can reach to a node there, like that is at least U, or earlier discovered node, that is S or T. So if we see that V, like through its descendants and at most one back edge, can reach to at least to U, or even better to an earlier discovered node, then we would say that UV is not a bridge. And if that is not the case, then we would say that UV is a bridge because V is the earliest discovered node that can be reached from V using its descendants and at most one back edge. So now we are in a position to actually formulate some conditions that we should check to determine whether an edge is a bridge or not. So first we should construct our DFS spanning tree, and then we should check each of its edges to see if that is a bridge or not. So we will be checking this edge, this one, this one, and this one. So we discussed that for any edge, like say like take like in general, for any edge A to B, we need to check what is the earliest node that is reachable from B. So we are interested in knowing the earliest node reachable of B, and we need to check if the earliest node reachable is at least equal to A, like the discovery time is at least equal to that of A or lower. So we need to check the earliest node reachable from B. We need to check the discovery time of that, like whether that discovery time is less than or equal to the discovery time of A or not. If that is the case, then the edge between A and B is not a bridge, because we know B can reach to A through its descendants and some other back edge other than BA, or it reaches to some other earlier discovered node which was discovered even before discovering A through its descendants and at most one back edge. So, and it will be a bridge if the earliest node reachable from B, the discovery time of that is greater than the discovery time of A. So this means the earliest node that is reachable from B was discovered after we have discovered A. So if we remove the edge between A and B, there is no way the subgraph rooted at B can connect to the rest of the graph, because the rest of the graph has A and all the nodes discovered before A. Now let's try to run the algorithm on this graph that we have here, and let's see if we get the expected result. So let's start constructing the DFS spanning tree by starting to do the DFS from node S. So the discovery time of the node S becomes 1. From there we go to the node T. Discovery time of node T becomes 2, and we also need to initialize the earliest discovered node reachable. So I will put 2 for T and 1 for S, and then we go to U, then V. So V will be discovery time 4, and we initialize the earliest discovered node reachable as 4. Then let's say we go to X. So the discovery time of X is 5. Then we go to W, and the discovery time of W becomes 6. Now we check for all the adjacent vertices from W to see if we are getting a better earliest reachable node than we have currently assigned to it. So one of the node one of the adjacent edge for W is the edge W and V, the edge between W and V, and V happens to be one of its ancestors. So we would compare the current lowest node really reachable of W and the discovery time of V, and we will take the minimum of those two. So V has discovery time of 4, as we can see from here. So W has 6, so the minimum would be 4, and then the other adjacent edge is the edge between W and X. So the adjacent vertex is X, but we see that from the DFS spanning tree, we also see that X happens to be the parent of W. So here we can actually keep one more row here called parent. So for s we can initialize this as say 0. For t it will be the discovery time of s. For u it will be 2, 3, 4, and 5. So these are the discovery time of the parent nodes for each of these nodes. So we see for w the parent has a discovery time of 5, and we see that 5 happens to be the discovery time of x. So we know that x is the parent of w, and according to our algorithm, while computing the earliest reachable node, we would discount the back edge in between the node and its parent. So we are done processing the w, because w has no other adjacent edges uh, to process so w has no other unvisited adjacent vertices. So we would backtrack to x. For x we have two adjacent edges. um, we check with w. W has the earliest reachable node as 4, and the current earliest reachable node of x is 5, so we take the mean and make it 4. And then the other edge we discount, because that edge happens to be the back edge going to its parent. So now we backtrack to v. V has three adjacent vertices, out of which u happens to be its parent. So I won't take into consideration the edge between u and v, because according to the algorithm, while computing the earliest discovered node reachable, we are discounting that back edge. So we will see what is the earliest reachable node for x and w is, and we see for both of them, the earliest reachable node has the discovery time of 4, and v has the earliest node as the node with um, the discovery time of 4. So we take the mean and it still stays the same. So now we backtrack to u. U has um, three adjacent edges, taking it to the three adjacent nodes which are s, t, and v. And let's see which one is the parent of u. So we visually see that t is the parent of u. We also see from this parent bookkeeping that we are doing, that the parent of u is the node with discovery time 2, and we see that t happens to be that node. So we won't consider the edge ut while computing while updating the earliest discovered node reachable from u. So we would look at v and s. V has the earliest reachable node as 4, and u already has 3, so we would take the mean, and it stays the same. Now we look at s, and we see that s happens to be its one of its um, ancestors. So we take the discovery time of s. The discovery time of s is 1, and we take the minimum of 3 and 1, and we make it 1. Now we are back to t, and t has two adjacent edges. S and U, and we see that S happens to be the parent of T, so we don't take that age into consideration, we just look at U, and we see that U has lowest reachable node as 1 and T has currently 2, so we take the minimum and we update it as 1. We are now back to S. S has two um, adjacent edges. So I look at T and I look at U. I see what is the earliest discovered node from U and T is and take the mean of that. So I see that for both it is 1, so the mean would be 1, and then I um, so I take the mean of 1 and 1, which is 1, so it keeps unchanged. So now in this DFS spanning tree, um, for every edge we need to see, for every edge present in this DFS spanning tree, we need to check if the condition for an edge to be a bridge holds true or not. So let's first take the edge S. So for edge ST, we see what is the discovery time of edge S, and we know that we would take the edge, we would present the edge in a way that the first vertex happens to have discovered before the second vertex. So if I say edge ST, that would mean that in the DFS spanning tree, S was discovered before T. So we would look at the discovery time of S, and the discovery time of S is 1, and then we would look at the earliest uh, discovered node really reachable from T, and that is also 1, and we would see if the discovery time of S happens to be less than the earliest node reachable from T or not. So we would see if this holds true or not. If it holds true, then it is a bridge, but we see that this does not hold true, so ST is not a bridge. Next we go to the edge TU. The discovery time of T is 2. The earliest discovered node reachable from U is 1. Then we see if um, the discovery time of T is less than the earliest node really reachable from U or not, and I see that that is not the case. Next we look at the edge EU V. We see what is the discovery time of EU, and we see that the discovery time of EU is 3, and then we see what is the earliest discovered node reachable from V, and we see that it is 4. Now we see if um, this relation holds true or not. We would see whether the discovery time of EU happens to be less than, I mean strictly less than, not less than equal to. So whether the discovery time of EU happens to be less than the earliest discovered node from V or not, and we see that it actually holds true, which means UV is a bridge. Next we will move on to the next edge, which is Vx. The discovery time of V is 4, and the earliest discovered node reachable from X is also 4. So the condition for the bridge does not hold true for the edge Vx. Next we go to the edge x w, the discovery time of x is 5, the earliest discovered node reachable from w is 4. Then we try to see if the condition for xw to be a bridge holds true or not, and we see no, 5 is greater than 4, so the condition does not hold true. So we see that the algorithm works perfectly fine, and we were able to determine that uv is the bridge. I have uploaded the working code for the algorithm we just discussed in the website thealgorists.com. So please go to this link to access the working solution that we have there. So if you go to that link, you would land on this page, and this page has a whole lot of more information about finding bridges, as well as the working code. And if you want to look at the other algorithms we have in this website, then feel free to go to the link algorithms and data structures, and you can see there are a lot of algorithms that you might be interested in learning. And we are adding new contents every month. It's always a pleasure discussing algorithms with you all. Please do let me know if you want me to make a video on anything specific that you want to know about. I will see you in our next video. Till then, take care and stay safe.